My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 555. In this lecture, we will try to understand deep multi-layer perceptrons. So, before we learn about deep multi-layer perceptrons in this chapter, I want to give you some historical perspective on what has been happening since 1980s. Deep learning is changing so fast. Let's get some historical perspective which gives very good sense of why we are doing and what we are doing. So in the 1980s and 1990s, almost till 2006, not only 2006, almost till 2012, till that time you have one of the big breakthroughs in deep learning. About almost till that time, mostly what people were trying to do was people were trying to build two or three layered networks, maybe two or three hidden layers. One of the biggest problem with this is vanishing gradient problem. We already discussed vanishing gradient problem. The biggest problem they faced was vanishing gradient problem, because this ensures that you can't build extremely deep neural networks. Yes, as what is the reason? Because of vanishing gradient problem, you can't build extremely deep neural networks, as we saw in one of the previous lectures, isn't it? This is just one problem. There are other problems, like people had too little data, isn't it? A vanishing gradient problem. And another problem is too little data to operate with. If you have deep neural networks, you could have thousands of weights, isn't it? If you have deep neural networks, you could have thousands of weights in your deep neural networks. When you have thousands of weights, and if you don't have millions and millions of data points, what would happen? It could be very easily overfit, isn't it? It could be very easily overfit. Yes, it could be very easily overfit, because lots of weights, lots of parameters, thousands in a model. And if you have too little data, it's very easy to overfit, isn't it? Is it not? Lot of shallow neural networks which are very popular in 1980s, 1990s, even up to early 2000s. We had two or three hidden layer networks. We had little data to operate. In 1990s, or I can say pre-internet era, isn't it? The second problem, what is the second problem? The second problem is too little data. The second problem is too little data, and the first problem is vanishing gradient problem, and third problem is too little computing power. Remember, when you have thousands of weights in deep neural network, updating these in every iteration, what do we have? We have mini batch of data, isn't it? In every iteration, what do we have? We have mini batch of data that you send through the network, and you update your weights using this mini batch. You compute your gradients or derivatives using this mini batch, and then you update using then you can update using those gradients, isn't it? From each iteration you calculate mini batch, from mini batch you will calculate gradient, with the help of gradient you will update, isn't it? Now if you have thousands of weights, each iteration will take lot of time, because you have thousands of weights to update. So in one iteration it takes so much of time. Imagine how much each epoch will take, how much multiple epochs will take for your model to actually converge epochs. You need multiple epochs, isn't it? But because you have too little computing power. Remember, in 1980s and 1990s, we did not have a lot of massive computing power, the massive computing power that we have now. Because of this, it took too much time to train these models. These three are most important problems. There are structural issues like vanishing gradient. Of course, we had too little data because of internet issues, and too little to compute also. But what happens in early 2010, by the time you reach 2010, things change a lot. We had lots of data thanks to internet, and lots of internet companies like Google, Facebook, Amazon, Extra, and we have a lot of labeled data, isn't it? Because of these internet companies, we have a lot of labeled data. There are competitions like ImageNet, which are extremely popular in 2010, where you have millions of data points which are labeled. So having access to high quality data, especially labeled data, because of internet companies. First point is we have lots of data because of internet companies. Second point, we have type of computing environment. So there is a sim called GPU, graphic processing unit. So what we typically look at in computer is a CPU. So there is a new type of computing infrastructure called graphic processing unit. GPUs are actually designed for gaming, and one of the largest company that makes GPUs is actually a company called NVIDIA. NVIDIA makes extremely powerful graphic cards. GPUs are also called graphic cards. So what happens was in 2010, computers were becoming extremely very powerful, because in addition to extremely powerful CPUs, we also started getting extremely powerful GPUs, primarily for the purpose of graphics or gaming, because we have much more higher resolution monitors and screens. And NVIDIA provides some of the best GPUs, and what researchers were figured out was GPUs are very good and very suitable, and they are suitable to the needs of deep learning algorithms. They were super useful. Lots of data, computing power, and new algorithms literally created modern deep learning. If you just have new ideas and algorithms but don't have enough computational power or lots of data to train, is useless. So these three things literally created modern deep learning phenomena. Not just one. You have new ideas, new algorithms. We have new types of computers that can speed up training by almost 100 times, isn't it? Speed up training by almost 100 times as compared to simple CPUs. We will see why GPUs are powerful and all of that in the next chapter, when we actually going into programming. We have lots of data because of internet. These three things together, not any one of them, created all these modern miracle called deep learning. What are those three things? Lots of data, computing power, new algorithms. There is also one philosophical difference that's happening right now is modern deep learning algorithms. If you recall classical machine learning algorithms, if you look at any classical machine learning algorithm, SVMs, the SVMs became very popular in 1990s. Random forest in 2000, boosted decision trees in 2000. All these systems are actually first they build great theory. First they build great theory, great mathematical theory, and then they do experiments. So lots of these classical machine learning algorithms started at universities, where people build mathematical theory. Universities are research centers where people were build all the necessary mathematical theory, and the experiments were done to justify these things works. Path is first build the theory and do experiments. So what happened in modern deep learning is this whole thing is got inverted in modern so what happens in modern deep learning is that the whole thing got inverted. People realize that building mathematics, building new theory is very hard while performing experiments. Given that you have advanced computers with GPUs, given that you have lots of data, people said let's experiment lot of things. Earlier people used to do theory then experiments. Right now people actually do lot of experiments then theory. People try to try a lot of things. This is the engineering approach of doing things. A lot of new ideas in deep learning in the recent past, they are coming from great universities like Toronto and Stanford, of course, also coming from companies like Google, Microsoft, Facebook. These are actually internet companies contributed fundamental ideas in machine learning, in traditional machine learning. I never see fundamental contribution to the I can say these are the companies, Google, Microsoft, Facebook. These are the companies which contribute a lot to this deep learning. I request all of you to go through this lecture. It will give some historical perspective. In my next lecture, I will discuss about one important concept in deep learning known as dropout and regularization. Thank you very much.